Welcome everyone. My name is Jose Daniel Muñoz. I am the head of the Simulation of Physical Systems group at the Department of Physics of the National University of Colombia. The goal of the group is to develop and to apply novel numerical methods for the simulation and modeling of phenomena in science and engineering. And we work mostly for different methods. First, discrete element methods and molecular dynamics. Second, Lattice Boltzmann methods. Third, cellular automata. And fourth, Monte Carlo simulations. In discrete element methods and molecular dynamics, we have worked mostly on granular media by developing new procedures, combining the good things of disks that you can simulate the interactions analytically and polygons. And we have also used them to simulate molecular motors like the ATP synthase. In granular media, we had developed in collaboration with colleagues from Australia new methods to simulate polyhedra in 3D with different shapes, but by rounded the polyhedra with circles. That allows to have circle plane contacts that are possible to simulate and to analytically. So you can compute for the energy and other different things. And with these particles, we can simulate soils, for instance. Also, we have studied fractures, for instance, in bamboo, and by simulating first in finite element methods and later on with discrete methods, the how bamboo breaks by drying, and we found that there are two different behaviors. First, if all bonds break at the same threshold, so you have that everybody breaks at the same time. So if you have, but if you have higher disorder, so a broader threshold interval for the bonds to break, so you will have that the system breaks in a different manner. And the transition from the first to the second is a phase transition. We developed that in collaboration with Professor Ferenc Kuhn from the University of Debrecen in Hungary. We have also worked on statistical dynamics of granular media, both for the volume ensemble proposed by Edwards and for the force network ensemble proposed by Schneider and Teich in Holland. And we have found that both of them follow a similar behavior. So it's possible, for instance, to find basic elementary volumes and elementary force to describe the degrees of freedom of the system. So this is as an intent to describe granular media from statistical dynamics, so from first principles. We have also simulated elementary SIs in soils, for instance, the automatic compression and other ones, in order to establish relationships among between the microscopical level of forces and the macroscopical level of constitutive equations for the soils. And we have also studied capillarity and percolation, and also other models for fracture in bamboo. The second method we use is the Lattice Boltzmann models, who are a special kind of cellular automata. So you divide the space into cells. At each cell you have some vector velocity vectors, that transport you to the neighboring cells. Traveling on these directions, you have what are called distribution functions that are the variables of the system, and that if you think, for instance, that it was a fluid, these are the probabilities to have molecules traveling on that direction. With these quantities, you can compute the macroscopic fields in a fluid, for instance, the density and the momentum. With those macroscopic fields, you can compute for the equilibrium functions. And the evolution rule is to compute new distribution functions as exponential decay to the equilibrium. And then later on, all these new quantities are transported to the neighboring cells. By choosing the right equilibrium functions, you can reproduce the desired partial differential equations, for instance, waves, fluid mechanics, electromagnetic fields, and diffusion. In waves, for instance, we in collaboration with Miller Mendoza from the ETH in Switzerland, we have developed how to simulate the wave equation in generalized coordinates, and we use them to simulate the cochlea. We have also implemented Lattice Boltzmann for shallow waters to simulate the Ciénaga Grande de Santa Marta, that is a very large coastal water reservoir in Colombia that is very broad, something like 400 square kilometers, but is just 1 meter deep in average, and is fundamental for the fishing and the water reservoir on that area. We have also simulated water reservoirs when you have temperature stratification. So we need to simulate convection also. And we have developed a Lattice Boltzmann method to simulate Magnetohydrodynamics as two fields. So two fluids, sorry, one fluid for the ions and one fluid for the electrons. And these two fluid equations plus Maxwell equations in vacuum, so simulate, for instance, magnetic reconnection. That is a very crucial phenomenon, not just in the magnetotail, but also in the solar flares. And by following the same direction with Miller Mendoza, when he was my former magister student, we proposed, for the first time, a complete Lattice Boltzmann to simulate the Maxwell equations in media. And this method is 10 times faster than finite differences and uses 3 times less computer memory to reach the same accuracy. We have also developed recently a Lattice Boltzmann model to simulate the advection diffusion equation in generalized coordinates that reproduce experiments and simulate Hilbert channels. This technique of using generalized coordinates allows us also to maintain isotropy and to increase the resolution in specific places, as finite elements does. And it allows us to take advantage of problem symmetries. We have also used Lattice Boltzmann to simulate hydrodynamic instabilities, capillarity, boundary layers, erosion, and the electromagnetic potentials in 3D. The third method we use at the group is our cellular automata. And for instance, you can use cellular automata to simulate diffusion. This is a very simple model. You divide the space into squares. At each square, you have particles traveling in 4 different directions, and it goes as follows. At each time step, each cell choose at random if it rotates 90 degrees, 180 degrees, 270 degrees, all the field remains in the same position. And all of them made the same at the same time, but with different random numbers. And this automaton simulates the diffusion equation in the macroscopic limit, and you can show that analytically. So we have used them to simulate, for example, the GABA synapse in the amygdala. So and our simulation reproduces experiments with high accuracy. But the main application we have used to cellular automata is the simulation of car traffic. What is a cellular automata for a cellular automaton for car traffic is very simple. You divide the streets into cells. Each cell can contain a car, and each car measures the gap to the car ahead. And according to an evolution rule that is common for all cars, each one decides if it speeds up, brakes, or changes the line. We developed a model for Bogota like 15 years ago. And with this model, we were able to reproduce the fundamental relationship between flux and density. And we found, for instance, that the highest flux was much higher than expected, so 88 cars per minute for a two-lane street. And this, I have to say that the same quantity, for instance, in Los Angeles is 64 cars per minute. So, and what is that? Because we drive here in Bogota very close to each other and very fast. So these results had a great impact, and we were reviewed in Nature and in Scientific American at the time. With this model, we have also studied the effect of individual behavior. For instance, what happens if you have mixed traffic, so buses and cars, and what is the difference between the case when all buses use the bus stops and when they stop everywhere they want. And we found that stopping in bus stops can duplicate the flux. We have also studied, for instance, what will be the optimal behavior to face the problem with one car stops in one of the lines. And we found that it's not 1-1, as is usually expected, but is 4-1. So it's better when you give the right to pass to the blocked cars only once each 4 times. We also use our model to simulate a BRT system. So it's similar to a metro, but with buses, as the one we have here in Bogota. And so to do that, we also took into account the proposed behavior for the buses when they reach and leave from a station. And we found that, for instance, that the cars doesn't maintain the distance. Let's say that a bus is traveling every 3 minutes, but at the end of the road, you have that buses have disorganized, and you can have longer waiting times, as longer as 15 minutes, for instance, just because buses have to take times to reach the same station. We have also used these models in 2D and also on nets to study traffic jams that usually is a phase transition between free flow and congested flow. But there are some basic models to study that. For instance, if you think on a square lattice, as in Manhattan, uh, one very simple model proposed for that is called as the Big Hamilton-Levine model, when you have only cars moving to the right and moving to the north. And what was expected was just a phase transition, but they found that there are also a three phase, some intermediate states when you have this this pattern of local traffic jams. And with my PhD students at that time, we were able to find that this is because the system is anisotropic, and then you have not just one but two phase transitions, and this explains why we obtain that behavior. Um, and finally, with this method, we are able to simulate whole cities, and that was done in collaboration with Marta Gonzalez, previously at MIT in Boston, but nowadays at Berkeley. Uh, fourth and last, we have used Monte Carlo to simulate radiation in medical physics. So one of these works, for instance, was to simulate the kidney radiosinovectomy by using rhenium 188, and that was done by Luis Carlos Lagares, and by using NMR images together with GM4 to compute to compute the doses. And what we found is that really the main point here are the NMR images and the post processing, because by using one sequence to take the images, or to using different by using different post processing, you will find a different volume and area for the for the liquid, for the synovial liquid, for the capsule, and then it changed completely the effectiveness of the treatment. So I would say that all this work has been possible because many students have done a great work by by researching these problems, and also because of the collaborations we have with different researchers and professors in Switzerland, in Germany, in France, in the US, in Canada, in Hungary, in Australia, in Portugal, and all around the world. So thank you for your attention.